we're going to talk about, let me put it here, second moment. I'll tell you in a minute why we say second moment or moment of inertia, or you might see it as area moment of inertia. All right, so let's clear something up first before we go further, right? The idea of moment, right? We have or put it this way, we talked about moments, right? For 2.5 weeks we were talking about moment. Now what is this, and what does this have to do with the concept of moment we learned before? All right, let's just clear that up, because the naming is very similar. We need to talk about that. All right? So moment. Now moment can be used in two different ways. In engineering specifically, let me put it this way. In engineering, moment is what we were talking about before. Something that we had a force. The force creates a moment about a specific point. Remember that whole story. Basically, in a very, very simple term, moment is something that makes something else rotate, or at least we want that thing to rotate. Right? Let me just put it exactly the way I say it. It's not a definition, like a formal definition, but it's just to distinguish that from the other concept or other moment that is not in engineering exactly, but it has come to engineering, or it's part of what we use to solve problems, but it has a different I would say it has the same name but different meaning, right? So something that makes something rotate. It's a very, very crude way of defining it, or at least we want to rotate, right? If you have a beam, for instance, like this, I might be able to draw a better one. So let's say we have a beam, we have a piece of rod, you have a rod, piece of rigid body, whatever rigid body we have. Moment is something that is, this is moment, right? We talked about this, moment or torque. Let's put it this way, moment or torque. Right? It's trying to rotate this object. Now it can be because of one force, moment about a point, or it could be because of a couple. So what is this new idea of second moment of inertia, or area moment of inertia? This meaning comes from mathematics, right? It's not exactly part of engineering. I would say the terminology is coming from mathematics. That's the right way of saying it. Mathematics. So what is that? It comes from this equation. This is the definition of moment in mathematics. An integral from -infinity to infinity, x minus c raised to n fx dx. Basically, what this is a function of x multiplied by a distance x minus c. Think about the distance axis x. C is just a constant, so x minus c is just moving that origin or wherever the distance is. So it's a multiplication of a function by a distance, right? This is the function. This is the function. This is the distance This distance is raised to a power n, and then we integrate it. That's basically the mathematical idea, right? The math. It comes from mathematics. It's definition of moment. Now, depending on the number we raise the distance to, we have first moment, we have second moment. We can just go up depending on what you're doing or which part. If you've studied or you take statistics, you'll see actually moments there. That's specifically in math. Now, so if n is 1, for instance, if n is 1, we call this the first moment, right? First moment. Right? But like when we were calculating, I mentioned that when we were calculating centroid of a shape, remember I said the numerator basically was first moment of area, that qx and qy. Right? That's first moment. Example would be when would be the numerator of the fraction we calculate to find the centroid of an area. Right? Remember, we said x bar is integral from 0 to some x final x f x dx. Basically, that's what we do, right? X, the area divided by integral from 0 to xf fx dx. And that fx, in that case, we can just consider that as when we were dealing with area was x. The denominator, for instance, was integral dA, if you remember that. The numerator was let me draw it here. It's probably easier instead of just talking about it. If you have a function like this in a very general form, x fx, and let's say it has some, draw it like this, and this is x from 0 to xf. This area, we want to find the centroid, right? The center where it is, it's located as x bar, at x bar, and we can find x bar that way. But what I'm trying to say is that this part is basically first moment of area. First moment of area. Now, what we have here is when is equal to 2, right? Second moment, or second moment of area. So if n is equal to 2, and pay attention to the first one. First moment of area is basically a distance x multiplied by a function fx, and we integrate that in x direction. So that is the definition of moment when n is equal to 1, basically. Right? Now, when n is equal to 2, right, this becomes obviously second moment. What does this give us? So we write it this way. We say second moment is, let's say ix, we represented with I, and second moment about one specific axis. Let's say, let me draw some rigid body here, some random body, x. This is y, And let's draw some rigid body like this. And this is an element in that body. Let's say small element there. dA with the area of, if the area of the whole body is A, the area of the small element is dA. We take a small element, then let's say the small element is located at X bar, or X, sorry, or X distance, and this is at Y distance. And also in terms of radius, it's this distance is R. So we defined the moment of any area about, or second moment of air, moment of inertia, area moment of inertia, or second moment of area about x-axis as integral y squared dA. Is that is distance y to raise to a number 2, n is 2, multiplied by a function, right? Think about dA as fx dx, similar to what we did for first area moment of moment of area here, right? You could think about this as dA. Think about this as dA. Second moment, that's how we define second moment about x axis. Second moment about y axis would be integral the distance raised to 2, because then it's 2 dA. So let me write them here. This is moment, I'll just go with moment of inertia because it's easier to say. But remember, you see all these names: second moment of area, second moment, area moment of inertia, second area moment of, sorry, area moment of inertia. So moment of inertia about x axis. This is moment of inertia about y-axis. All right. And finally, we have polar moment of inertia, which is basically they represented with J. You also see it with you'll see it in different ways of representing, but basically it's r squared dA. The distance r, right? Now instead of x and y, we are finding it with respect to the origin. So r squared dA. Still, it's a second moment of area, right? But the way we define it is different. So this is polar moment of inertia. So 3 new concepts we introduced here. This is moment of inertia about x-axis, moment of inertia about y-axis, and polar moment of inertia. There's a relationship between them, actually. Polar moment of inertia is equal to the summation of those two, ix plus iy. So they are related. Now, one more thing I'm going to define, and we'll look at a couple examples how to calculate. So these are very important. Goes back to, again, when you design a structure, right? You will see it, and again, in solid mechanics, in machine design, very often, very frequently, when the design engineering structures, we do care about these when we calculate different types of stress in our structure. What is a stress? Stress is basically force divided by area, right? We are in this course, we only care about force, right? Later on, you will see area comes into play, force divided by area would be stress, and then that's how you connect the design into the material you want to select to make sure that can handle that much stress. That's kind of an indicator for your design, or some parameter that you can use to choose the right material, the right structure, right design. But that's down the road. Here, what we want to do is just we want to get comfortable with area moment of inertia or moment of inertia, right? Because you are going to use it and you're going to calculate it. I would say use it more than calculating it. This is engineering, right? We usually have things in tables. You'll take machine design, and you'll see a lot of things are tabulated. You just have to be able to find them. So here in statics, we just get comfortable with the concept, right? And what it is and how can we actually calculate it with simple shapes. And then the same story like centroids, how can we calculate for a composite shape, right? Because those are obviously come up during engineering design. So it might seem a little abstract. As I said, it comes from mathematics. It has nothing to do with the moment we were studying before, but it has a lot of applications when you design structures and you want to make sure that the structure can handle the loading or force applied to it. So these are the definitions, right? One last thing that I want to define related to second moment or moment of inertia is the concept of radius of gyration, right? Radius that you also again see in a lot of design handbooks when you want to choose some specific radius of a material. If I can write gyration. Now what that is, well, think about radius of gyration this way. Think that you have a rigid body like before, some rigid body. This is the element there, dA, that the whole thing is A, and this is dA, right? And once you know that distance, right, from here to here, if it's y, and then the value for your ix is basically integral y squared dA, right? That's moment of inertia about x-axis. Now we define kx, radius of gyration about x-axis, as, oh, this is the equation. Let me write it first and I explain what that means or what physically it means. Square root of ix over area. So if you calculate ix for that area divided by area, square root of that would be kx, radius of gyration about x-axis. Now, what does that physically mean? It means that this is the radius or a distance, that is better, a distance from which if you condense this whole rigid body into a very, very thin, very long area, right? The area of this rigid body, let's say you're going to condense it. This has some area. You're going to condense it into something like this, very long. Let me change it, put it somewhere else. Very long, very thin area. The area of this is still A, right? But now it's distributed in a very different way. It's like very thin bar, very long. Radius of gyration is the distance that if you put this very condensed thin area away from x-axis, will give you the same moment of inertia about x-axis as the rigid body. So again, this would be radius of gyration. Let me put here, let's say this distance. I'll call it kx. So radius of gyration is the distance that if you put this very, very thin, like one, almost a line area away from x-axis, you will get the same area moment of inertia or moment of inertia as your original rigid body had about x-axis. That's radius of gyration. So you can define it the same way for y-axis, right? Ky would be also Iy over A, meaning that if you had a rigid body and you can condense it or you can reform it into, I'll put the rigid body here. And let's say this is some dA and this is x, right? This is x. Then your Iy, moment of inertia about y-axis, is integral x squared dA. Now, if you can condense it into very, very thin, just put it here, very thin area, radius of gyration is basically the distance that you have to put this new equivalent area away from y-axis to get the same moment of inertia about y-axis as you had for your rigid body. That's the concept or the meaning of radius of gyration, what it is. Now, what is the point and usage for that? Again, in design, you will see that we work with, especially structural engineers, they work a lot with radius of gyration and area, moment of inertia, moment of inertia. And the same story for KO. Let me change this to JO, and I put this O here. So I'm just gonna make it so it's easier to follow. This is O. Then KO would be square root of JO or IO, depends on who you talk to. They use different terminology over A. And that, again, meaning is if you have an area like this, some area like this, and this is your R, and this is dA, because your JO would be integral R squared dA. If you can condense it into a very thin, let's see if I can do it and draw it here. These two should be overlapping, so not overlapping, should have the same. So let me just make it a little thicker like this. If you can condense it into a very thin ring, that ring should be placed at the distance KO to give you the same polar moment of inertia about point O as your original rigid body.